very happy to have Sri Kulkarni visiting us from Caltech, where he's the George Ellery Hale Professor of Astronomy and Planetary Sciences. Sri asked to keep this informal, so I won't belabor you with a long introduction, but he is the most recent recipient of the Shaw Prize, and the citation, I think, does a pretty good job of spanning the depth and the breadth of Sri's work over the years, including the discovery of millisecond pulsars and brown dwarfs, and major contributions to supernovae and GRBs, and of course, the creation of ZTF. Seems like he's gone back to his roots, and he's working on the ISM now, so without further ado, Sri.
Okay. Yeah, so it's almost 7 years ago I decided to step down being running big things. I was a director, long-serving director of the optical observatories at Caltech. And I said, well, in my last phase of career, I should do the opposite of everything I've done. So no more fundraising, write single author papers, and do some theory. So that's, I always thought if I had nothing else to do, I'd do theory. So anyway, that was my fallback plan. And I suspect for many of you, this will soon become your fallback plan, actually. Okay. But you have to choose. Well, as some of you know, I switch fields about every 5 to 10 years, and I've become quite experienced in switching fields. So one of the things is first you have to choose a field to switch into, and then once you've chosen that, I always offer to teach in that course. It's like surgeon, first time it's good for the surgeon, bad for the student patient. Second time it's evil. Third time it's not so great for surgeon. You know how many operations you want to do again and again, right? Anyway, so I decided to teach ISM, and this work came out of that. In June, I finished teaching ISM for undergraduates, and I have a friend, Chaz Beichman, and he said, oh, a month from now we'll have this big JWST press release, and aren't you excited? I said, no, I'm sort of old, and it's exciting, but I have no new ideas in exoplanets and high redshift galaxies. Then he said, oh, you become such a curmudgeon as you grow older. I said, yeah, that's true. But it did make me think. And I have a nice backyard, and I went and I had a glass of red wine. And nothing happened. I had another one, and I said, okay, what can I do with JW that's very different from the usual exoplanets and high redshift? And that's the advantage of teaching, because your basics allow you to do new things. And I think that's the disadvantage of having a Marx Planck system in my mind. Okay, enough of that. So I want to talk about the warm ionized medium. So I'll start a bit of history of how we actually came to recognize this medium, because many people, I think, are not really aware that this is one of the earliest things that in the studies of the interstellar medium that actually got recognized. Many of you will immediately say the 21 centimeter line. Yeah, it's true, but this is not so far from that actually. So here it is. This is a paper in 1961 or 62. And I sort of like this old style. The whole paper is one page in Nature. And this is from Tasmania, where the ionospheric frequency, the plasma frequency is low, the lowest. We can have one somewhere, I guess, the equivalent would be in Canada somewhere, Penticton area, the northern pole. So Reber had founded this low frequency observatory in Tasmania. And what this shows, and so there's a small group there, and what this shows is here is the galactic, looking inside in the inner galaxy, is just a brightness temperature or intensity, radio intensity, as a function of frequency between few megahertz and tens of megahertz. Okay, and the point made by this group of radio astronomers that it actually turns over. Okay, that was the observation. Okay. And a remarkable paper, Fred Hoyle interpreted this correctly, in the sense now, 60 years later, this is the exact interpretation we have, which says that this turnover is due to free absorption at low frequency, And says therefore there must be some plasma with a density, very low density, scale height, electron column density of 10 to the 20. And in fact says this requires the ionizing radiation point B stars, because the ionization power required is extremely large, and therefore we had no choice. You can't use hot white dwarfs or other such things. Anyway, that is 1962, and but it wasn't really noticed much by sort of the ISM community. Go back and look at the old ISM books, you won't find as much a mention of this. Okay, well, a few years later we had the discovery of pulsars, and the first thing that became very clear is that no matter which pulsars people are looking for, they always show distortion. Therefore, this medium is really pervasive. Okay, again, this didn't have much effect. Even actually, if you look at the three-phase model of McIndoe-Stryker, the homogeneous medium is a footnote. It's called three phases. It doesn't have the homogeneous phase. It's simply shown as the ionization sheet of the warm neutral medium. Okay. Okay. So this is by end of 60s, astronomers are aware that there is this pervasive medium, but with no good idea how to do this. It's one thing to say, oh, B stars will do it, but they need to propagate the Lyman continuum, which has very high optical depth. So you need a high porosity, and that's not obvious how to do it, and still not so obvious. Okay. But the next big thing that happened was due to optical astronomers, particularly one specific optical astronomer, Ron Reynolds. Okay. Who absolutely pioneered this field by bringing in Fabry-Perot techniques to the study of the interstellar medium. Okay, so Ron's thesis at Wisconsin was actually how to use Fabry-Perot, which were already being used by Rosalind Scherf at Wisconsin for aeronomy studies. Okay, we have bright HR from the geocorona, and so which was discovered in the 61 or something. Actually, of all the places, Soviet Union. I don't mean in a bad way. This really requires very precision echelon, so it's not an obvious thing you'd immediately associate. Anyway, then I think this finding of widespread H-alpha really started taking hold. And you can see that. So here, for example, here's LMC. You can see, well-known H2 regions marked here, but from your eye, there's some very diffuse matter. It's not, so it's not like you really have to think very hard. Okay. And you can, in fact, it has a much larger scale height. There's an Edge-on galaxy 891, and this is an H-alpha on the left side, and then the contours to show you that this is in fact not just pervasive, but as good in the lower halo. This in fact becomes a dominant component. So Reynolds started a major program at Wisconsin called the Wisconsin H-alpha mapper, WAM. It's a Fabry-Perot, 1 degree in beam, very sensitive, 0.1 Rayleigh. So I suspect many of you are not very familiar with Rayleigh. And I have a point to make here. I think it's extremely important when you look at a problem to make sure that the units are properly matched to the situation. By which part of that is, in fact, the unit should be chosen so that the typical value is like 1. Okay, because I think I've been convinced over my decades of research that I don't think we understand numbers beyond less than 0.1 and more than 10. We have a very good feeling for those. After that, you can start losing the value. So if someone tells me the mass of sun is 2 times 10 to the 33 grams, I think it means actually nothing to any of us, but maybe for some of you, but for me it's nothing. Okay. So I won't give you the usual units, which is megajansky per steradian, because I think it's a completely useless unit. I don't think anyone would even have it translate. So you have to go to a unit that is very natural to this field and invented by astronomers, which is the Rayleigh. And the Rayleigh is 10 to the 6 divided over 4 pi photons per square centimeter per second per steradian. Okay, and why is this nice? Because most things that matter to astronomy, the answer is about one really. So for example, if you go to a very dark side, let's say Mauna Kea, a moonless night, clear sky, then the background in the optical band is about 1 or 2 Rayleigh per Einstein. Okay, so you can immediately start computing from this. Anything someone says, oh, I will use a 1 meter, then I can start computing in my head already the limiting magnitude right away from that. Okay. Okay, so this goes down to 0.1 Rayleigh in H alpha. Okay, Rayleigh is in photons, so they integrate over the line. And the main workhorse is H alpha, though there are thousands of square degrees mapped in the, what I'll introduce these lines called nebular lines of nitrogen plus and sulfur plus. There are a few other optical lines you can actually see. Oxygen 2 and oxygen 3. They didn't do much. Now here's the outcome of the WAM project. And I'm sorry, the temperature bar is missing. But you actually can see, even at the north and the south galactic poles, it's roughly about a Rayleigh or so. Okay, that's the, and you can roughly translate Rayleigh to an emission measure. It's temperature dependent. Okay. So it is, so H alpha, widespread H alpha is actually, no matter where you look, you will see this galactic H alpha. Okay, so as I said, even though this was introduced in as a name in the 3-phase model of Mikio Stryker, which came about in '77, almost everything in that paper about the ionizing power, the total amount is incorrect actually, because this medium really was not fully appreciated as having an incredible demand on the energetics. So in our own galaxy, maybe as much as 1/4 of the total OB for EUV emission goes into ionizing this medium. And the challenge is not so much it's 1/4, the challenge is how do you actually, if you have a classical strong sphere, then all the Lavin continuum is all processed, there's a sharp edge. So you need to drill holes through this, or you have to have some porosity. Okay, that's the challenge. Okay. Okay, so it's now accepted as a phase of the interstellar medium. Really, we should talk of 4 phases of the ISM. It is this phase that hosts most of the ionized galaxies. So when you look at a star M51 or LMC, you may be impressed by the H2 regions, but altogether the amount of mass they have in ionized gas is only 1/10 of what else is in the diffused medium. Okay. It's very pervasive. The filling factor of the WM can in fact compete in settling the halo to even more than what you might call the coronal gas or the hot ionized medium. The interiors of supernova remnants, which is the gas you tend to see in X-rays. The amount of radiation that you lose that finally leaves the disk of the galaxy sets the stage for the circumgalactic radiation. Okay. And so people interested in CGM, the boundary condition of how much is leaking from this medium is an important input. Because the CGM is not just ionized only by the intergalactic radiation. Okay, and finally, it's either a nuisance or a diagnostic. There's a whole cottage industry of interstellar scattering and scintillation, which you really can use to either study turbulence in this medium, or you can turn it around and make good use of it for other things. So for example, if you want to, one of the fun uses of scintillation and scattering is to show superluminal expansion of gamma ray burst afterglows. Okay, as the radio afterglow expands, the scintillation changes from diffractive to refractive, and you see that very clear transition. And so from that you can work out what is the angular size. Okay. In fact, the older one, which is interplanetary scattering and scintillation, is the whole basis of the Cambridge surveys, which is the survey that led to the discovery of pulsars. And for a long time, IPS was the way to measure the angular diameter of radio sources. Okay, so what are the ways to study this medium? Well, obviously, pulsar dispersion agent is a major one, but it's a point measurement. You can add a magnetic field, and then you can make rotation measure, and then recombination radiation, which is H alpha. Okay, that's sort of where I'm specialized. And then the optical nebula lines, the main workhorses are forbidden lines of nitrogen plus and sulfur plus. And there are other lines that have not been as well studied, O2, O1, N1, and O3. Radio recombination lines is very important as you go in the inner galaxy. The sensitivity difference between H alpha, which is a recombination line, as is this, is enormous. In optical techniques, you can, with some effort, go to 0.1 really. But the radio lines, you'll be hard pressed to reach 100. I mean, you really have to at that point be integrating tremendously long time, even 100, okay. But in the inner galaxy, the gas is rich, and the optical radiation is extincted anyway, so that's, and there's a whole new boom here in radio recombination lines, which was very, popular in the 80s and then sort of died, it finished its thing. The reason is that multi-beams in radio astronomy have really increased the speed at which you can observe this. So it's a field that's come back again. Then I would sort of call these a somewhat newish techniques, and the one that I will focus on is the mid-infrared fine structure lines. And I won't talk much about two-photon continuum. And then also we'll just only mention here that in my mind there's a really nice thesis topic here to use these new low-frequency arrays, but not in what I call as the low band, using low power convention. So below the TV band, okay, not above. So when I say low frequency, I really mean low frequencies, okay. It's more than 20 megahertz, don't talk, okay. It has to be like 10 megahertz, and you have to wait till the sun becomes less active, because that sets the ionized plasma frequency. But we have a bunch of these facilities, so we can actually start doing this with these new techniques. Okay, so a little bit of a background. It's like teaching my ISM class, and that's the point of teaching, is that it opens some new ideas, especially when an innocent undergrad asks you some question, and then you say, I really don't know that. But you may not admit to the student, but then you can go and think about it. Okay, so when the terms nebula lines, aurora lines, these are very old terms, okay. They simply reflect their origin. The nebula lines were first seen in astronomical nebula, okay. And the aurora lines were first seen in the aurora. That's all there is to it, okay. Okay, so let's understand this. So if you look at these growth train diagrams, for example, you can look at oxygen, okay, oxygen 2, then you call the transition, so it's in the same electronic configuration here, they're all 2s2, 3p3. It splits in the same configuration, therefore obviously they're forbidden because you're not changing the parity here. So these transitions have to be either magnetic or electric quadrupoles, so the A coefficients are very small compared to the other transitions. So from the ground state to the first excited state, those are what is nebula lines, except in auroras, which are, you have energetic protons from the sun, electrons, and so you can excite, so those transitions from the second to the first excited state called auroral lines. Yeah. And these are the lines that you can actually study. In particular, this is a well-known line, especially for extragalactic astronomy. Okay, but this is a half shell, therefore the ground state is not split. But if you go to ones where the shell is not half or full, okay, you get the splitting of the ground state, and that one of the most famous fine structure lines is of carbon plus at 157 microns. Okay, this is a famous C2 157 micron line. Not as well known is the equivalent of nitrogen 2. I don't know whether I have that here. Maybe somewhere. Okay. Okay. So this is a famous one. Let's see. Another one here. Yeah. Then the other famous lines are like oxygen 1. You see these, and then far infrared fine structure lines. Okay. So they came in the 80s. But if you go to higher Z elements, so remember it is oxygen, carbon, nitrogen. Those are the highest 3 elements. Okay. Oxygen is maybe approaching 400 parts per million, and nitrogen is about 100 parts per million. Okay. But if you go to the higher Z elements, that the ground state fine structure lines going to the mid-infrared. Okay, and that it's been well known, but it's not been used for the study of diffuse ISM because we didn't have the capacity. The JWST is very large. The metric here is A omega R. Okay, A is the area of the telescope, omega is the field of view, and R is the spectral resolution. Okay, and JW wins in A. It wins in R. Omega is small. The field of view of the MRS system is only about 10 to 20 square arc seconds. Okay, and you should compare that to the 1 degree beam of the WAM. Okay, so let's do a little comparison. The optical lines, while they're very well known, being studied, the biggest strength is they're convenient. It's an optical band. So we have a lot of big telescopes to study. However, they're both sensitive to extinction and temperature. If you look up, the very fact that optical means you excite them, about 1 or 2 EV or so. So the exponential matters here. The far infrared lines, the way, these are the lines that are driving like ALMA and the high redshift science. Main value is it's very high abundance of C, O, and N. Okay, they're insensitive to extinction and temperature. The disadvantage is carbon gets depleted. It's very hard to, you have to make some assumptions of the depletion of carbon into the grains. And also they have very low critical density. The A coefficients for these is typically 10 to the minus 6 per second. So as you increase the density of the H2 regions, it saturates. So you don't, this goes back to the problem that old millimeter wave astronomers are familiar with. It's like if you have a saturated line, how do you convert that to mass? Okay, and there's a whole industry of people using ALMA and other things. The mid-infrared lines, they don't have the sensitivity to temperature. They're only 1,000 Kelvin, so it's easy to excite them, especially in ionized regions. And these are neon and argon, actually noble gases. They don't condense into grains. Sulfur also doesn't condense so easily into grains. Okay. So you don't have to worry about any depletion and unknown things. And because the A coefficient for this is higher than the far infrared lines, you don't have this saturation of the lines. So what you see is every excitation. Okay, so with that, let me go into the work that I ended up doing after that first press release. Anyway, so because I'd been teaching, I had a good command of all these lines, and so after the press release, I said I had my 2 glasses of wine, I realized, okay, you can actually start seeing these lines in JWST. Namely, whenever you use this IFU spectrometer, it's called the MIRI MRS, which is the medium resolution spectrum. It's an IFU. The field of view varies. It's an IFU. The field of view varies on as a function of wavelength naturally, but you can see it's not. It ranges from 3 by 3 arc seconds to maybe 7 by 7 as well as long wavelengths. Okay, it's an amazing IFU. It goes all the way from about 4.8 microns to almost 28 microns. Okay. In 3 settings, you can get the whole mid-infrared band. So here it is. So let's look at these mid-infrared lines. Here's neon. By the way, neon is not very, the abundance of neon is not very different from nitrogen. It may not be so obvious, but neon is actually very abundant. You'd all think that nitrogen is abundant, so is neon, okay? Then sulfur and argon are less so, but their collision strengths are larger, so they sort of make up for that. The point I'm trying to make here is that if you want to ionize neon, it's 21.6 eV, okay? In contrast, if you want to, let's say, ionize nitrogen, it's 14.5 eV. So when you see neon, you really are, neon 2 or neon plus, you really are probing the Lyman continuum quite a bit away, actually, from the Lyman edge, 13.6 eV. So one of the questions in this field is, okay, you have these OB stars, the radiation comes out through these porous H2 regions, and then as they propagate, it's a very messy radiative transfer problem. You could argue, in fact, that the photons closest to just a bit about 13.6 eV will be more absorbed because the photoelectric cross section goes into -3. And then you want to know what about helium, and that's been, we still don't know what fraction of helium is actually ionized in the diffuse ISM. Okay, the radio recombination lines suggest it's less, it's about 0.1, the optical suggests it's 0.5. So if you can use these ratios, you can start inferring the spectrum of the diffuse ionizing field, which is an extremely important input for all these models that people are doing in galaxy star formation. Okay, so the line ratios can probe ionization, the spectrum of the ionizing field. Okay, so these are the calculations that I did where of saying how much is the, are these detectable? And you can see in an hour of midi-MRS observations, these are good SNRs actually. And so I called up Chaz, my friend in JPL, and said, get me any data, it doesn't matter because the diffuse ISM is all around us, and these lines would be detectable. So he got a calibrated data. This is a 6 magnitude star. They're doing something for JW calibration, photometric calibration, and they had an off beam. It's, in the mid-infrared you take on beam and off beam. Radio astronomers know this technique very well because you don't want to mess around with what else is in the sky, right? That's why I do on minus off. But I was interested in the off beam because the on minus off would subtract away the very signal we're looking for, which is pervasive. I don't know, this is one of the first few, and which is public, so I sent it to me. And this, where is this in the sky? Well, the sky, it's the source is here. It's extremely tiny, and you can see here. You have to divide this by 4 to get the emission measure. Oh, 22, sorry. So it's very faint, and here's the H alpha seen in WAM data. Okay. In this case, the data, initial data was, they're not fully understood all the electronics. It was very messy, but we know what we're doing here. We are looking for an unresolved star because of the spectral resolution of 3000 of the midi-MRS, the galactic lines are unresolved. And you know the rest frequency. So you can look at this and then you know what is the solution. Okay, obviously there's some fringing, some sort of a high frequency noise, and obviously there's some weird baseline variation. Okay, so right away you know the solution is Fourier techniques. Okay, so Fourier transform thing, take or chop off the low frequency, high frequency, and when you retransform it back, well, lo and behold, it's exactly where we expect. Okay, so that's in fact the detection of neon 2, similar things in sulfur 3. Okay, so so this led to so right now with the graduate student, second year grad student, I've been working where we basically have all this data, right? So I think the data sets are now about 300. So the point I'm making here is that no matter where you look, you'll see these lines, and of course, so the off is signal for this project, and the part I really love, as some of my old friends know, I have by instinct, the more popular field is, the more I dislike it, even if it's a good field. Okay. So like high redshift galaxies, I truly intensely dislike it, And the nice thing here is that you can spend hours doing some midi-MRS observation to look at redshift 10 galaxy or whatever. But the one thing you can't miss is what's happening right here at your nose, which is a galactic ISM. So in fact, you'll see this everywhere. And so that's what we've been seeing. So what this shows is as a function of galactic latitude. That's not so important. So what this shows is the NE2, neon 2 emission divided by the H alpha emission from Finkbeiner's, whatever the thing that he provides on the, which is a combination of WAM and SHASA and V-test and so on, okay? So it's a nice tube that is so this is basically neon 2 over H alpha, okay? Now, simple theory will tell you, what it should be, and that's the dashed line, okay? So many times we find, it agrees, and then there's some places it doesn't, it disagrees very much. And before you think, wow, this huge neon abundance, there's a simpler explanation. Namely, the resolution of this H alpha can be as bad as 1 degree if there's no other data other than WAM, or maybe as good as maybe 6 arc minutes if it is just the smaller surveys. Whereas this one, the neon 2 here is just 3 by 3 or 5 by 5 arc seconds. So that shows their structure, which is not a surprise, okay? And I'll address that a little later. Okay, but which in itself is a whole new game here of actually studying this medium at arc second resolution, which for many people who do FRPs and pulsars, they're salivating at the prospect that we can actually start studying these small structures. However, let's go back to what we can do with this. So you can now look at this neon ratio, neon 3 to neon 2, neon 2 to sulfur 3, and run cloudy and show these plots as a function of what's called the ionization parameter. The ionization parameter has many names because it comes up in different contexts. It's basically the number density of photons to the number density of electrons, okay? So, or baryons if you wish, is a usual way it's stated. And things like H2 regions in this scale would be like -2, -1, the bright planetary nebula and so on. It's a log scale, sorry, so the one I'm showing is log scale. And we believe that the warm-ionized medium is actually very low ionization parameter. And so the brightest points that we are seeing here obviously have a high, so there must be actually the structure, we must be seeing some structures where maybe it's a hot white dwarf. Again, there's a whole bunch we have to now start doing this. But we can already see that if we had, there's some are upper limits, we don't see in one but not in the other. But it's already now spanning the -3 to -4, okay. One thing I will tell you that if you go and do a simple elementary calculation, you know the throughput of milli-MRS, you know the sky background, so you should be able to compute what is the fluctuation in the sky, in the continuum. And we're up by a factor of many, sometimes up to 10. That means we don't really understand this instrument very well, okay. Now a lot of sins get forgiven when you do an on-minus-off, which is why people like to do on-minus-off, because that's one way to get rid of systematics, okay. Anyway, so the rest of the year, we'll do a deep dive and try to understand why we want to reach the theoretical photon limited noise in this instrument. And I like this. It's it's one of these arcane technical problems, but I like doing that sort of stuff. So I think there's plenty of opportunity here to actually go much fainter than what we're doing right now. Okay, so in order to determine abundance, okay, so, and I see this as an interesting new little game, because if you ask how do we know what is the abundance of elements, the classical techniques are like you look at H2 regions in the inner galaxy to outer galaxy, and then you do the optical lines like nitrogen or sulfur and or oxygen, and that's fine, except that those lines then you have to correctly model the temperature, which is fine. I think with H2 regions in our galaxy, you can actually do that, because you can use a variety of techniques. The advantage of these things is these are noble gases. There's no temperature dependence, and there's no extinction. Okay, so I think in due course, this will in fact become a very good technique to metallicity gradients in galaxies. However, for our own galaxy, there's a little problem, unfortunately. If you want to get, what we want is on the same angular scale with the milli-MRS aperture, we also want H alpha, okay? Okay, there's one problem, which is when the sun has set, it's a dark night, at midnight, when the sun is on the other side, if you look up, you will see H alpha. It comes from it comes from the exosphere of Earth, and it's basically the Lyman beta that is fluorescing and producing H alpha, okay? By the way, the term geocorona was actually the name was given by Shosky, who immediately understood upon hearing the discovery in 61 that this hydrogen has to come from a high altitude, hundreds of kilometers above, because you don't have atomic hydrogen at sea level or anything even low enough. Okay, so here's what happens is if you look up at midnight, you'll see a very strong, narrow H alpha. The geocorona, roughly arises maybe at 1,000 kilometers or more, and the gas is hot there, about 1,200 to 1,500 Kelvin. That's why the lines are fairly narrow. In contrast, the WIM is at 8,000, so the lines will be broader, and also rotation curve broadened. So you have to actually subtract that So you need a spectrometer which is got large A, big telescope, large omega, large field of view, and very high angle spectral resolution so that you can actually subtract this line or resolve this. Well, that's getting very demanding at this point. Okay, you're firing on all cylinders by demanding A, large omega, large R. Fortunately, we have one. The Keck Cosmic Imager actually offers you very high spectral resolution. So if you use this as a grasp, it's quite good. For example, Muse at VLT is also very good, similar grasp as, but you can't resolve the geocorona with that, and so you have to do additional modeling. But it's still very impressive that WAM, which was commissioned in the mid-80s, has a grasp which still beats everyone else. Of course, that's mainly because it has a very large opening angle. Okay, as an example of sort of as a teaser for future studies, one of the fun things that what we do is once a month we just download all available the new data from Miriam RS, and start looking at things, especially the off fields, off beams. And here's one where it was very bright signal. Okay, you see all these lines. Okay, I was surprised, and then it turns out here the PI team was apparently interested in studying the very inner region of M83, and they thought, oh well, let's go far away from the galaxy and put a background. Okay, but apparently not far enough, because if you really go and look very hard with in galaxy FUV, you would actually see there's a very faint outer spiral arm, and so if you image that field, I think there's in fact some very faint H2 regions. But right away, all we have to do is now do some KCWI H-alpha studies, and right away we have the metallicity at the very outer edges of the galaxy. Okay, to me it's astonishing the power of this instrument. The off beam itself is so you get two papers for one proposal. That's no good, right? You get it both on minus off and off. Okay, and these are very bright signals. They're very impressive actually. And it's, by the way, it's at the right redshift. This is 0 redshift because that was our interest. Apparently we don't see much from our own galaxy, but we see a lot from this very outer arm H2 region. Okay, and I'll try to now wind up by talking a bit about, so this got sort of me interested in this idea that we can start studying these diffuse gas with JW. I don't, the power of this IFU are not appreciated. So when we were looking at some data at low latitude, I was struck by how rich and how obvious, you can just look at the spectrum and immediately say photo and not collision. I'll come to that. So now let me talk of something called the dense warm-ionized medium. So the warm-ionized medium is what we talk within a kiloparsec 2 or something. But if you got very low latitude, let's say along the galactic equator within plus minus 30 degrees of the galactic longitude, it's been known since the late 70s, the radio recon lines from Effelsberg, one of the early results, that you see the radio recon lines are quite powerful, or quite detectable. It wasn't, in some sense, not a surprise that Herschel, which also had an IFU, found great evidence. So this is a survey done by Goldsmith and Lang and others. They basically were doing this C+ key project where you just go at the equator and you every degree or so step through and either use a HiFi or PAX to study these lines of nitrogen 2, which are natural to study here. Okay, so nitrogen 2, okay, that's a ground state. It is split. Again, you have two lines. Famous line is 205 microns, and there's another one at 122 microns. Okay. Remember that unlike these, the other lines I talked about mid-infrared, the A coefficients here are large. Sorry, so very small. 10 to the minus 5 as opposed to 10 to the minus 2, which means these are very sensitive to temperature. As you increase the sensitive to density. As you increase the density, the lines saturate. Okay. Anyway, here's an example where everywhere they looked in the inner galaxy, they were finding this is a position spectrum plot, and that's just the image. They're finding basically N2 205 micron emission. Okay, I've converted this detection, so you can take that N2 and then use the ratio between the two lines and compute the density, and that turns out to be typically 30. Okay, so this is a different kind of medium. It's somewhat dense, and you can convert that to to a dispersion measure, and you'll find and compare that to pulsar dispersion measures, and you find that in fact this gas is a significant fraction. In fact, these emission seems to contribute half the C plus emission in the inner galaxy. Okay. So the C plus emission is a little more complex. So you get C plus emission now from obviously the PDRs. You get C plus from the neutral medium, warm neutral medium, or cold neutral because it's easy to excite it, and it looks like you get C plus from this other sort of weird thing. So the basic idea here is that finally it's been resolved when Langer took Green Bank radio recombination lines, and they basically say that these you can now see what's happening is these large H2 regions in the inner galaxy, they're really the porosity is very clear. They actually, this is sort of the near halo of these H2 regions, and that's what you see in this high density gas, which doesn't obviously absorb all the radiation because that's what's left to do the warm ionized medium. Okay, but it is a surprise, and to me it's a surprise, and I don't know what people working in this field at high redshift, how exactly would they be interpreting the C plus emission when it, my problem with extragalactic studies, you just get one pixel and then you have to make stories about it. Whereas in the galaxy, you study things really, okay, but anyway, it's an interesting, so if you're going to look at some JW, some random field here, which is an off beam, it's close to the equator in the galaxy. Well, look at this. It's really astonishing. There are some lines of iron, which I won't talk about. I'll talk only with the principal lines here. I can tell you right away by looking at this, and because I looked at this enough, this is photoionized gas. Okay, and I'll make a small kind of thing, perhaps of interest only to some radio stones in my next slide. So for this, you can't use H alpha, but we can use the radio recombination lines. And there's as I said, there's a big industry with FAST and with GBT now, where we have very sensitive. And so right away with this, we can start determining abundance in the inner galaxy. Okay, and we expect it to be there'll be more neon in the inner galaxy. Okay, this is just an aside. When this data came out, Guy and Walker from the Herschel, they proposed that this dense gas is collisionally ionized. Okay. Now, if you're not an ISM person, you say, "Wow, what's the difference, collision and photoionized? It all looks so diffused anyway." Not really. There's a huge difference between the two. And they wanted, and they were trying to explain a very arcane thing in centimeter wave radio astronomy called extreme scattering events, or sometimes known as Fiedler events. Okay. But with that one spectrum, in fact, a little paper can be written, which is that it's not it's not collisionally ionized. So let's look at this again. If you teach a course, that's a good thing, So if you look at collisionally ionized, in this case neon, okay, as you increase the temperature, you go from neon 1 to neon 2 to neon 3, and so on. Okay, here's the crossing point, right? Half of the gas is neon 1, other half is neon 2. Okay, and now some of you may remember your ISM class. It happens only at 1/10 the ionization potential. You may not remember, but you can't get. It's very hard to get neon 2 and neon 3 at 20,000. Impossible. So with that one spectrum, you can actually refute the idea that this collisionally ionized gas is abundant in the galaxy. Okay, so let me summarize. I would say we have a new mill. And for this mill, we have grist from the media MRS. Anything you observe with media MRS, thank you very much. We'll be using it. And then we have started a program to use this powerful IFU spectrograph, which is somewhat unique in the world right now, which has got both a large telescope, very high spectral resolution, and a decent field of view, 20 by 8.5 seconds, which may not sound much to you, but I'll tell you this is a very massive spectrograph worth tens of millions of dollars. And then we can start probing the small case structure of the ISM with this. And then in the inner galaxy, we can use this new radio recon lines and Herschel data to study the dense warm ionized medium. A mission called Prima is under development right now. This is for the far infrared. It'll be like JWST, except it'll be it'll be like Herschel, except it's a cooled Herschel, so it'll be Herschel on steroids. So there are lots of, little papers to be written on this. And with that, I'll stop.
Thank you, Sri. That was great. So we've got to clear out for ITC lunch, so maybe just a few questions.
I was really struck by your MH3 example, and just thinking about like the outer arms of these galaxies, they're almost close to their halo almost. And so, what do you? Just sort of naively, I would have thought that those extragalactic cases are kind of great because you can see the ionizing sources and you can see the resulting gas, and but it seems like the galaxy itself is your primary focus. So what am I missing, or what?
No, nothing. It's a fine thing, For me, the closer the better.
Yeah, and I mean, I take your point about it's right here.
Yeah, no, it's fine. No, it's just there are a few such things we are now finding.
Yeah.
Yeah, the other one is a starburst galaxy, and it's very clear that right out in the halo, there's actually an outflow that you sort of don't see. But if you look very carefully at Deep Chandra image, at least it seems to me there's a very faint X-ray emission. So I think this is, how do I put it? Either you can do this as an experiment, because it's so powerful, or you can just wait and someone will do, especially this galaxy is easy because people are always trying to, there's a limited range that they can do the offset or the off beam, okay? And so I think this will actually be quite interesting.
For all the previous close.
Yeah, or you can, I'm just saying the power of this, I was astonished myself that you can see such strong signals in what appears to be the last faint spiral arm. Yeah.
Wow.
This is very cool. I think it is cool and encouraging to see that more people are finding interest in the galactic interstellar medium in its various phases. There is LVM, you mentioned it in passing, which will systematically scan the disk. And so one of the things you can do with your approach is you can add depth information, right? You can combine it with some estimate of the velocity of the kinematic distance estimates from velocity curves. So you can make a 3D reconstruction of the electron density of some of the other features that you mentioned. Is this, so two questions, is this something you plan to do also? Because I think you can do much more than what you have had the chance to talk about today.
Yeah, so right now...
the second part maybe of the question is, what about the local bubble? And so I was very much wondering about your latitude dependence of your measurements, because there seems to be very little.
Yeah, so one of our goals is to start using these large lines of sight to construct the vertical distribution, in this sort of classical approach and convert that. And because I think there's a transition from we all agree that the filling factor of the warm ionized medium, maybe it's few 10% in the plane, but I think by the time you get to 1 kilopascal, it's 100%. Okay, so we want to understand the radiation field, the intensity. So I think it's within reach. The problem right now is we detect with sort of your typical 20-minute observation that whatever people have observed, we are detecting only in about 40% of the cases. But if we can understand the systematics, and there's huge room for improvement here, and I don't have a new idea, but in some cases the systematics are about 10 times the photon noise that we expect. So I think once we solve that, I think we can start actually doing many of these finer studies. And I'm pretty sure I think if we solve that, I think we'll actually be helping all these other observers, because right now they do this on minus off to sort of sweep this end of the world. But the goal we have set out is, can we from first, in some sort of a first principles way, construct the sky as seen by JWST in the mid-infrared. So it's a work in progress. So I think maybe a year from now we can probably improve our sensitivity by a factor of 5. Then we'll start competing actually with WAM at that point.
Okay, great. We should end there. Shree's around today and tomorrow, so email me or him if you want to meet up. Let's thank him again.